Okay, hi guys. As always, let's just give a few minutes to see if we have anyone else joining us. So yeah, let me just get everything ready in the meantime, and while we wait for other people like that might be coming late or something. By the way, while I get everything ready, please don't forget to download your data files and all of that. I think there is only one data set that we're going to use today, but make sure that you have your R session ready, all the setup and all of that we always do, working directory and everything before we start. And we will start in 2 minutes, I think. I always like to leave a few minutes to see people that might be coming late. In today's tutorial, I anticipating that it's going to be quite short, like from what I could see in the questions. So I think we will have some time also for questions at the end. So if we want to hold into all the questions by the end, we will have plenty of time to work them out. Yeah. And let me paste the link of code share in the chat that's there. So you guys will have access to the codes that we are going to use today. All right, you can grab it from there and put it in an R script like I have here. And yeah, download the cwb.csv dataset in your folder. Change your working directory, all of that. I don't put how I changed my working directory here on the R script because if you run it, it's not going to work on your computers, right? Every path is different for every computer. So, just go session, set working directory and choose directory, and that way you can navigate your computer. I think I'm working here in tutorial 8. Yeah. And that will prompt this setwd command. Okay, I think we can start now. Code share that's ready there for you. So it won't, please don't like delete anything from there or anything. It will be up there, I think, for a day or so. So make sure that you grab it and save your R scripts. So today we're going to discuss. Oh wait, actually, yeah. Before I forget, don't forget that you guys have a submission for project 1 next week, next Tuesday, 4 p.m. So again, it's not midnight. Don't get fooled by that. I actually like that Eric moved away from the midnight deadline because you wouldn't have people that like are 11:55 trying to upload everything. Make sure that you do this with heaps of time and don't don't miss on the marks there. Okay, so yeah, make sure that you go to to Blackboard and upload everything. So today we're going to discuss tutorial 8. By the way, if you're wondering, there is no tutorial 7. We didn't have any tutorials before the break, so you didn't miss anything. Eric just decided to keep the numeration, consistent with the week. So this is week 8, so that's why it's tutorial 8. Week 7, we didn't have a tutorial. We did have some class, a lecture, but yeah, no tutorials there, so you wouldn't find like a recording or anything. And I was going to mention, and yeah, so there is no recording of that. We just had consultation last week, like for the people that wanted to double check stuff before the break. So don't worry if you feel like you're missing on anything. So today we're going to talk about how to model volatility. So one way to do this is with GARCH models. GARCH stands for autoregressive conditional heteroscedasticity models. GARCH is just generalized autoregressive conditional heteroscedasticity models. What these models do, like you guys remember when we had this time series that like most of the times, that even if they seem to oscillate in the in the around the same value and they won't drift over time and all of that. Sometimes the spikes that they show are not even. We will expect that band to be quite even. Sometimes you have like these huge peaks, these very low points, and then just some points in between. That as an indication that you guys remember the assumption that we make for the ARMA models to work. It violates the assumption of constant variance, right? It clearly, the variance is not constant over time, so we need to see how we control that. These models start with a model that we represent the means with. Most of the time, it's just an ARMA model, but you can, I think, yeah, you can also use ARDL models, but for the intents and purposes of this course, we will model the means of an GARCH model using ARMA, right? So this is the structure of the ARMA PQ, like general ARMA that we have studied extensively throughout the semester, right? Oh yeah. What's the difference? The difference is that we no longer assume that these residuals are white noise. We now bring some structure to those residuals. That structure being the errors being split into an unconditional variance, which is a white noise component to it, and a conditional variance, which is something that changes over time. And this is where we will capture the behavior of, or we will control for those changes in the variances over time, right? In these huge variations. So the way we do that is how to model the conditional variance. The conditional variance will have like we take the residuals, we square the residuals, and when we model it with lags of those square residuals, that's what we call the arch component, just lags of those square residuals. And when we also use lags of the conditional variance, that's what we call the GARCH component. Two things to note. Oh yeah, it's here. The coefficients I put, like I use the same notation. I use alphas and betas, but that doesn't mean that this number is this same number, right? They are estimated separately, so the estimates will be different. I just forgot to change it to, I don't know, gamma or delta or something like that, but these numbers are not going to be the same. And very importantly, you can either have arch components and GARCH components or only arch components, but you cannot have only GARCH components, okay? GARCH components need to be accompanied with ARCH components. And in terms of the notation, we call the number of lags for the GARCH component as P and the number of lags for the ARCH as Q. Even if ARCH come first, we leave that as Q. So the notation, we put, we will use GARCH PQ or ARCH Q, depending if you have or not have GARCH components. An ARCH Q, of course, is equivalent to a GARCH 0Q, right? You don't have any P, you don't have any lags of the conditional variance. That is equivalent to an ARCH model of whatever number of lags you put in there. Yeah, please don't consider models that only have GARCH components without ARCH components because we cannot have those. All right, so let's move to the questions. Let me split to RStudio. Okay, and now here on RStudio, please make sure that you guys have these three packages up there: Forecast, Dplyr, and GARCH. So you can just do a little bit of a search here with the magnifying glass button here. Dplyr should have it there, and GARCH is also there as well. Whatever package you don't have, you can use install.packages to install it. I think the one that we haven't used before is GARCH. So you can use this. Let me paste it in the chat. Only if you don't have it in your list. So I was scrolling, where is it? GARCH. Yeah, if it's here, don't run the install packages. That's why I don't put it in the code share that I put there for you. Because if you run a package that it's already installed, R will ask you to restart your session. It gets a bit messy. So just to drift apart from that, to stay away from those problems, we just mentioned the packages that you're going to use. If you call for a package that you don't have installed, R is going to say, hey, install it first. So you kind of noticed that you might not have everything that we need to move forward. All righty, let me put up the questions. Where is it? It's impossible to find anything in this new Windows. All righty. So we have worked with this time series before. We have the share prices of the Commonwealth Bank. We have 10 years of data, of daily data. That's like roughly 2,605 business days. So that's the number of observations that we have. So let's call that share price, let's rename it to be Y, and let's check if that log share of prices, like how does it look like, if it looks like it is like it's following stationarity or not. You know what we always do. So we start by loading up the data. The data set CWB.csv should be in your folder. So like I have it in here, make sure that you have it in your working directories. So we can run line 7 and my data will be put up here. So these prices, this Y, it's already in logs, so that it's transformed already. So we can just plot it. Wait, we are going to grab this value, this variable Y, and assign it to an object called Y, just so we can call here Y without having to use the $sign anything. So this is a bit of a convenience step that we make. Our variable is stored here in Y, so we can use line 13 to plot it. We will plot it with dates. We extract this information of the dates here into a variable called date. Yeah. Please note that the format here is month, day, year. That's the American format, which is a bit different than the one that we use. So we need to tell R that this format is month, day, year, and is split by slashes. So that's where we put the slashes. If it was separated by dashes, we would put something like this. So it's important to give R all the tools so it won't make a mess. So sorry, I forgot to run line 9. So that information is stored here in the object date. So we will plot that time date variable with the y variable in a line plot. And we get this plot here, which will tell us two things. The first thing is that investing probably in the Commonwealth Bank stocks was a good idea because it just went up, and then it had a little bit of a problem here, but in overall it was just kept going and going up, which is great, right? So so that's one thing. The other thing is that it's clearly not oscillating around the same value, so this variable will not be stationary. It's clearly trending upwards, right? So what we will do now, and that is question 2, we will plot the returns, the log of returns of this variable, and see what will happen. Remember, we have different ways to bring some stationarity to the model. And one way is by taking first difference of the variable. Another one is by calculating the log returns of that variable. So whatever we use, it will help. In this case, we are instructed to use the log returns. So we will calculate the log of that variable and find the difference. That will just make me think that this variable might not be in logs, which is what it was instructed in the, yeah, log of y. Well, we can do that anyway. So let me do log y as, well, the log of y. We will get the variable and we can plot it to see here. Just to test, it doesn't change too much. Technically, this is what we were instructed to do. So let me just update the code share for you. But yeah, it doesn't change too much. Anyway, it's still going up. It's more like it brought some the feature of the log of the logarithmic function. Now it kind of looks like a hump instead of just a straight line, but still. So let's just generate the log return. So that's line 18. R is put in here. So let's just plot R. And since we're doing the difference like of 2 points, like remember we have yt minus 1. We need to exclude the first point because we don't have a -1 point for the first point, right? So we will be having problems there. So we just leave the first point outside and then we plot it. And we get this graph here, which is way better, right? In terms of mean. Now it doesn't drift over time. It doesn't follow any trends. But as you can see, there is clearly a lot of heteroscedasticity here. We have some high peaks and some very low values as well. So we don't want that. Now we used to be very flexible with this bit, but now we know that we don't want that. So we need to control for this. Now, one thing that you should remember, you should gather from this, is that if the returns plot shows heteroscedasticity, that immediately means that there is also heteroscedasticity present in the variable in levels without any transformation. It's not like when you do the log and the diff there, it will bring this it will bring this behavior. It's just making it more visible, okay? But it's there. So regardless um, um, of the transformation that we make, we need to control for that variance that changes over time. Okay, for now, we're just going to push through. Let's not worry about the errors yet. Let's just identify an adequate set of ARMA models, right? Because as you guys remember from the slides that I prepared here, we need to model the mean, and then we will model the variance, which pretty much means what are we going to do with the conditional variance, right? If you're going to uh, uh, use ARCH or GARCH components or both, well, technically GARCH components includes ARCH, and like if it's appropriate to do so, right? We're going to test if that's the case, because we shouldn't be using models that control for heteroscedasticity there if it's not present, right? There is no such thing as an overkill here, so we need to be careful. So this is the selection code that we have used so far, right? We just are going to use combinations of P and Q from 0 to 3, so that's 4. That's why the matrix for the information criteria is a 4 times 4, right? Rows to store all of this information. And we are going to change that. Eric decided to use the indicator to where to store these coefficients using I, like as it is here, that it will separate by every 5 rows or whatever, but I can give you one that can work for you in your assignment, and is that if you start with an indicator I that starts at 1, and at every run of the loop, let me put it after everything, if at every part of the loop you just increase it by 1, at every run it will just go to the next and to the next and to the next row, so you don't have to worry about how to manipulate that combination of eyes. I think I deleted it. Let me check on code share that P plus 4 times Q plus 1. You don't need to worry about that. You just start with an indicator, an iterator if you must, and for every run of this loop, the iterator is going to be increasingly larger by 1. So this indicator will go to the next line. It's just giving you a tip for the assignment if you want. So let me just copy this. This is going to be in code share only, because I'm not allowed to change this, like when sharing the the script with you in like I always share it when the week ends. I won't be doing that. So yeah, actually we can try something. Let me run all of this, but let me change the name. Just bear with me for a second. I just want to make sure that I'm giving you guys like a code that will actually work. So I see ARMA 1. Okay, it's here. Now let me try the code that I share with you, just for, just to try. Well, goodness. Okay. So I created this matrix with both loops, and as you can see, it's the same information in both. So that loop that I gave you would also work, and I think it's easier for your own assignments. So yeah, by all means, just use it. It's in code share right now. Sorry, let me just copy something. Okay. Alrighty. So yeah, we know what's next. Just checking which is the best in AIC and BIC. So we filter by the best 10 in those models. We find the intersect between these two models. This is like the same thing that we have done so far. And we are going to use as our selected group, we're going to use AR1, AR2, MA1, which is not here, but it's in one of the best in the AIC, I think, MA2, and ARMA 11. So we're going to go with the simplest of models. Again, don't worry about model selection in this sense, as long as you come up with like a criteria how to do it. In this case, you can also like choose to use all these 7 models, maybe the first 4, whatever you choose, that will be okay. So don't worry about like what is the criteria here. Just worry about like actually how to create this. So you will need to change these indices here to make sure that you grab the models that you want. So if you're grabbing, I don't know, the first, like the best in terms of AIC, so you will put here, or the best 4, something like that. So you need to be careful of how to create um, these two items in here. And I'm talking about the assignment, right? If you just leave it as it is here, it might not be the models that you want. All right, next stop is checking the residuals. So I'm going to run the usual check residuals command that we have. We know that we get a few graphs in there, but we are going to focus mainly on the Leon box tests. So we have, this was the model selection, sorry. We have our 5 models. All the p-values are way higher than 0.05. So residuals are fine. We can proceed with these models without a problem. And again, I know that I might be speeding a little bit, but this is a thing that we have done the whole semester. So I think it's not, I think it should be clear. But again, we can check this at the end of the tude if you still have some questions. Okay, now what we're going to do is to test if the errors in the models that we selected contain ARCH or GARCH effects. So to do that, we're going to perform the Bruch-Pagan test for the presence of heteroscedasticity. The null hypothesis in this test is that there are no ARCH effects. So should we reject this test, that means that we should not model the conditional variance using the structure that we discussed earlier. It's the white noise, and we should not model it. However, while looking at the behavior of the graph that we have, it's very unlikely that these effects are not present, right? Especially with such high and low points. If it was something like here, something like this, it might be a bit far-fetched to think of arch-garch effects, but in this case, I think that they might be present. So it's better to test first. The first step is using, like, estimate the conditional mean using ARMA, as we have done, and store the square residuals, right, of each of these estimations. So we're going to grab this E for every combination here. So we have AR1, so that's just these 2 items, AR2, so that's these 2, MA1, MA2, sorry, MA1, MA2, and ARMA 11. So that's this with this, right? So we estimate all those 5 models independently and capture the residuals. So we store them and we plot them so we can get an eye, like we can give an eye test to see if the residuals are like that, if they are if arch or GARCH effects are present there. So what we're going to do is just generate an empty list to store those residuals, right? And for every model in the set of models that we selected, that's this N mods, we are going to go one by one and grabbing the estimates of the ARMA models that we have, capture the residuals and square the residuals and put that in this empty list that we have. So we're going to do that for each of the 5 models. And then we're just going to store a little bit of a title there. So when we do the plot, the title appears in here, right? So we are creating the string of text, which is going to appear in the plot. And we are also interested in seeing the ACF of these residuals. So let me just get ready. We can run all of these commands at once. So let me save here and run it. Ah, so it's already done. Look at that. Okay. So let me go back to the first plot that we have. And this is the first one. As you can see, the square residuals, again, those peaks that we saw earlier, by squaring those residuals, those peaks become more evident. So again, to find evidence that the arch or GARCH effects are not present, this graph should be like a band there without like huge high peaks like we have here. So having these weird points and most of them are not too high. Like you can see how most of the points are just probably below this height, and then it's still we do have a lot of, I like to call this hair, like weird hairs there. So it seems that it's evident. The ACF of that residual are also showing that they are autocorrelated, right? We have a lot of peaks here that are significantly different than 0. Disregard the first line as always, because that's row 0. We start with row 1. So these values, like the first 3, 7, even the 8, I think, are significantly different than 0. Then we have a lot of some of them. So that's evidence that heteroscedasticity is present. Same for the next model with the same thing in the ACF. AR10 has the same thing, all of these weird hairs. Same in the ACF. ARMA11, which is the last model, also has that behavior. Oh, sorry, it's not in order. This also, this behavior is also present. So this, having a square residual graph like this is clear evidence that these square residuals are like, it's very likely that this test will be rejected, that there is actually arch and GARCH effects present in here. So I hope that you guys remember the rule of thumb of like how do we do this eye test. The next bit that we're going to do is regress that residual squared variable, so to speak, and regress it at each of the different levels of lags of itself at every time. Okay, so it's not regressing it to 10 lags of itself, it's regressing it by 1 lag. So ET squared equals alpha 0 plus alpha 1 ET minus 1 squared. So we do this regression and we capture this Lagrange multiplier statistic, which is the number of observations times the R square of this regression. And we store that that statistic. Then we expand to 2 lags. So ET minus 1, ET minus 2. So we regress this and compute the statistic. Then with 3 lags and compute the statistic, and all the way to 10 lags, with computing all those 10 statistics. And we're going to compare each of those statistics one by one with the critical value from the chi-square distribution with Q degrees of freedom. So that means a number of observations minus the number of lags, the number of elements in the model. Don't worry, R will give us these critical values without a problem. And we are going to test. We're going to test row one by one to see. Sorry, we're going to test the null hypothesis one by one, and we will expect that if arch or GARCH effects are not present, then we will fail to reject in all the 10 lags. If we reject in a few, that it's enough evidence to confirm the presence of our arch GARCH effects. Now, usually, just giving you this. I'm sorry, this is a typo here. I went out like all the way to 10. And most of the times, like these effects are present, so this test is usually very conclusive. So it's something to expect in this case. So let's move to, actually, let's see what we have. Oh yeah, we now in question 5, we are going to do the test. So let's perform the Bruch-Pagan test. We're going to do this test with the square residual series. That you remember that we captured before for each of the ARMA specifications that we used. So these square residuals, what we're going to do is to store it in an object and create a formula for that. Because since we are increasing the number of lags at every run, we will start by regressing it on itself, like on 0 lags. Actually, that's this first bit. And then at every run of the loop, we are going to add the next lag. So then you will add the first lag, so that J will be equal to 1. So that's the first lag, then the second until the 10th lag. So with this paste function, we will be updating this formula. So we will do the regression of the square residuals to itself at a larger order of lags at every run, instead of having to copy and paste by 10 times and change the formulas there. So that's a very clever way of doing this. For every regression, we are going to capture the n, right? Because we are going to build this Lagrange multiplier statistics. So we are capturing the number of observations and the R square. So we build this statistic n times R squared, right? And we are also going to do the inverse chi-squared, like testing it. So the critical values are already there. This is giving us the test automatically of that Lagrange multiplier statistic to the chi-square critical value, and it will adjust the degrees of freedom to the number of lags at every run. So for only 1 lag, this Q will be equal to 1. For 10 lags, this Q will be equal to 10, and that is changed by this. And we're going to just check which is the, we're going to create a table to display these results of the Bruch-Pagan test in here. So whenever you're asked to do this code will be completely replicable. You will just have to set up what is your number of models from before. So n mods, sorry, that's in general in here. You will always be asked to do this for 10 lags, so that's there. Yeah, so this code, I would assume No, yeah, I think I'm almost pretty sure that is completely replicable, meaning that you can all copy and paste. Just make sure that you have nmods already created and E2 ARMA already there. Otherwise, it won't work, but just make sure that you have these two things done before. So let's run line 79 to 95, please. Make sure that you highlight everything. Don't leave like stuff in between because the code will not work or R will not do what we wanted to do. So we will run it. It's already there. Wow. Okay. So let's look at the results. Those are in the BP test command. So we have for each of the models. So the first model of ARMA is MA1 or ARMA01. That's the model in here. And it's doing the test for the 10 lags of the square residuals. Then we have MA2, all the 10 lags. Then we have 1, 0, 10 lags, 1, 1, and 2, 0 as well. So we have all our 5 models with the 10 tests in here. And I actually gathered this. I actually gathered this table. Sorry, I'm having technical issues with PowerPoint now. It's back. I gathered the two tables in here, and as you can see, the p-values are very low for every combination, right? So we will reject the presence of, we will reject the presence of we will reject the not presence of GARCH effects, meaning that we have evidence, sufficient evidence to conclude that arch effects are present in here, which is what we expected given the plots that we got of the square residuals. So that's good. And now what we're going to do is just estimating models, expanding it from the ARMA models that we selected, but now adding different GARCH specifications. So actually showing the slides, let me scroll all the way back. We are good up until this point. Now we're going to model. Now that we know that we should do this to the residual, we should split it into a conditional and unconditional variance. Now we're going to do model selection to what these specifications should be. Okay, so that's what we're going to do now with question 6. So let's program that. We have, let me close this. We have sorry, I'm just going a little bit ahead just to show. Okay, we're going to oscillate. So our ARMA models, I think that's why Eric decided to go with these simpler models that are kind of consecutive, and is that when doing the like adding the GARCH models in here, we can also iterate. So we're going to iterate from 0 to 2 lakhs of autoregressive components, 0 to 2 lakhs of MA components, 0 to 2 lakhs of GARCH components, and 0 to 2 lakhs of ARCH components. So each of these values, each of these lag lengths, so P, Q, Q here, and P here are going to be oops, sorry, let me go at this where we are going to oscillate from 0 to 2. For that, we are going to use this GARCH package. The only caveat with the GARCH package is that when we are estimating this model and we don't have any arch or GARCH effects, that's possible given the combination of the numbers. We know that these models are very likely not going to be a good fit. But numerically, those iterations are going to happen. So in order to prepare for that, when those two components are equal to 0, we should use the our FEMA spec and our FEMA fit commands. When they are not different, so this condition is not true, we will use the uGarch spec and uGarch fit of to do the process. So the split here with this if is the just to make sure that we use the right command to it. Okay. Other than that, this command, you will not need to change anything. The estimates of the ARMA GARCH models will be stored in a list that we create to be empty. The information criteria, you would be needing to be careful. 3 to power 4 because it's 3 times 3 times 3 times 3, right? If you were to go all the way to 3 lakhs, it would be 3 times 3 times 3 times 3. So sorry, 4. So it will be 4 power 4. But just as a rule of thumb, we never go above. It's very unlikely that an arch GARCH model will have more than 2 lakhs. So it's most of the time we don't have, I don't know, arch GARCH 5, something like that. It's usually something in between 0 or 2 lakhs in there. One thing that Eric actually found is that the estimation of a few of these combinations will cause R to struggle. So it will use the try command. If it couldn't find an optimization or a solution for a combination, it will just skip it and go to the next. Okay, so I would recommend to use this for your assignment if you're not able to estimate lags. I think it's for ARMA over than 5, something like that, but you do need to push forward because there is some models there over, I don't know, AR11 to AR15, ARMA 11, I don't know, 11.1 to 11.5, like, yeah, AR11 to MA5, something like that. So combinations above that, so it's not like you can only estimate a few models. You can estimate a lot. You just need to move past those that it's not possible to estimate. So I would recommend using this try function. Again, if you need help there, I think we can check that in consultation. So I'm going to grab from line 98 all the way down to line 146. Let me double check that this is the case. Yeah, line 98 to line 146 in the code share as well. So let me run it, and R will ask us to give it a minute to process all of those models because it's doing a lot of optimization constantly. So it will take a couple of minutes to do this. And if your computer is a bit old as mine, it's going to take longer than that. Okay, it's done now. So we have, I see in the section of ARMA GARCH. So these are the best combinations of models in terms of ARMA GARCH lags. As you can see, most of the times we have both Arch and GARCH models. You can see here how we have 1, 2, 1, 2, 1, 2. And we only have 3 models here that only consider GARCH, but not ARCH models. So these models will not be considered because it makes no sense. We technically needed to 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 program it, and R will keep it, will estimate it, but it's not practical. So we will just go with the first 36 models in this set. So that's what we're doing in here, just taking the intersection and grabbing the first 36 models in there into an ArmaGarch adequate set object and grabbing the indices as we always do. So this is the key part, I think, for the replication of these codes. When you get to this point, how to change this, how to change these indexes here so you can actually select the models that you want, right? The next step is to check the residuals because these residuals should be good, but there is a problem though. Let me just wipe this just for 1 second. Because we cannot use the like the traditional Young box test is not like no one has taken the time to change the the settings of or the parameters of the test in order to control for when we actually have as heteroscedastic models. It usually assumes homoscedastic models, so we cannot use it. So what we're going to do is just grabbing those models that are stored in this ArmaGarch estimates that we created as we progress through the loop. So the estimates are in that list, sorry, in that list. So we're going to produce the ACF for those estimates for only the indexes, so the first 36 models that we are working with. Yeah, and we are going to look at those ACFs and see if there is a significant different than 0. So we will be rejecting the null hypothesis of white noise residuals. So these ACFs will be stored in SACF GARCH, which is this list. I actually summarized it in the chat. Okay, this is model selection. Summarized in the chat. It's probably very difficult to look at, but if you're doing it at home, as I'm progressing, you can notice that none of these numbers is ever higher than 0.08, which I think is this first values. So it never is something 0 point something, it's 0.0 something. So that's good. That means that it's very likely, because usually, I actually dropped those, but usually those 95% confidence intervals are not larger than 0.1, are usually something below that. So having those results in here, like numbers that are never 0 point something, but 0.0 something, that's good. So that's as good as we have to check the residuals. The residuals seem to be fine, but we need to be careful because we can't actually test if those residuals are actual white noise or not. So it's not programmed to do that. Alrighty. Let's now move on to the last question that we have for today. Now let's estimate those models, those 36 models, and plot the estimated volatilities. So we're going to plot this HT. So we will see if there is significant differences in there. So let's grab those last lines here. What we're going to do is just plotting those ARMA estimates for the adequate set that is stored in this indexes indicator. This is just some strings there to create the title. So the title here, that text is going to be displayed but the important bit on this plot is here, right? We left the title so they are differentiable when we are exploring, because we are going to produce 36 plots, so we need to know which one is which, right? All right, so let's go and run all of these, and again I think it's going to take a minute. Oh no, it's already there. All right, so yeah, these are the models that we estimated, a combination of ARMA GARCH items. As you can see, look at how I progress through the graphs. They don't change significantly, right? They are just there. No problems here. It's the same. It's not the same, but it's very similar. And when we compare it, actually, let me plot the square residuals for the different models. When we compare, for example, this plot, like one of these plots to this one, you can see how these estimated volatilities, so these conditional variances, they are very similar to the square residual. So that means that we are like these models are effectively capturing these volatilities, right? You notice here the huge peak, then a couple of low peaks. Here, huge peak, then the couple of low peaks, then another huge peak, then a few little ones, then it goes like to the next one. So a few little ones, then the next one, then it goes to 2, and then a large one. And here they are, 1, 2, then the large. So they are capturing this behavior. So these models are good. We can use either of them because they are very similar. We programmed 36 models and the changes are not particularly significant. So, oops, sorry. So whatever model or set of models you want to use for forecasting will be okay. So that's good news. That our result seems to be robust for specification. So that's great. Let me just double check here my notes to see if I'm not forgetting anything important. No, that's it. All right. Thank you guys so much. That's all we have for tutorial 8. So week 8 technically will be kind of tutorial 7.